Good afternoon, folks. I have another challenge problem for us. This one is what I think is a really good practice and review problem because it incorporates about 4 to 5 different concepts that we've covered already and just kind of squishes them all together. So let's check out the problem description. We have this block A, the top one here, weighing 1.90 newtons, and block B underneath it weighs 4.20 newtons. And we're told that the coefficient of kinetic friction between all surfaces is 0.30. And what we need to do is find the magnitude of the horizontal force F necessary to drag block B to the left at a constant speed, given that both of these blocks are connected by this light flexible cord around a fixed frictionless pulley. So, there's a lot of tongue twister words kind of occurring in this last part here. And really all it's saying is don't worry about the mass of the cord and don't worry about the pulley. The only thing that we're concerning ourselves with are these two objects, block A and block B. That's it. So if we have just two objects, what do we do here? How do we proceed? Well, let's start by making free body diagrams, and then we'll go from there. So here's our free body diagram of block A. Remember, this is the block that is resting on top, and it's going to move to the right in response to block B moving to the left. So regardless of the horizontal movement, the weight of block A points directly downward. I think we can all agree on that. There's nothing special going on there. The normal force that's equal and opposite to this vector is the normal provided by block B pushing on block A. Okay? There's not a normal force on block A provided by the table, right? It's provided by it just sitting on block B. So that's kind of where this notation here is coming from. And that is it for the vertical forces, because block A is not, flying up into the air or going into the earth or something. So that does it in this direction. What about the horizontal direction? Well, we have the tension from that attached cord that pulls in the plus x direction. That's what's responsible for kind of pulling block A to the right in response to block B. And since the net motion, the overall motion for block A is to want to move to the right, well, that means if there's kinetic friction as a result of it grinding against block B, well, that's got to be pointing in the direction opposite to the net motion, which means it's going to be pointing in the negative x direction, like this. And so we have kinetic friction as a result of block B acting on block A. And that's it. That's all the forces on block A. What about block B? Well, strap in. It's going to get a little complicated here. We'll move on to block B very carefully and very slowly. So we can still label the weight of block B right off the bat. I mean, there's nothing crazy or special about that. However, there's another downward force that we have to account for. And what is that? Well, that is the effect of the normal force of block A pushing down on block B. Remember, we've got Newton's third law going on. If block B pushes up on block A, well, block A is going to push down on block B with an equal and opposite magnitude, right? So these are the two downward forces that are experienced by block B. What about the upward one? Well, there's nothing significantly crazy or different about the normal force with block B compared to anything else. So I'm just going to call it N sub B. Okay? What about the horizontal? We were talking about block B getting pulled on by force F. What does that look like? Well, force F points in the negative x direction, so it looks like this. And we said that the overall motion of block B is to get pulled to the left. So the frictional forces that we have to account for all have to point in the direction opposite to that. They have to point to the right. But first, let's include the tension. I almost forgot that one. That is pointing in the same direction as block A, simply because it's kind of attached in the same location for block B as it is block A. So nothing too wild going on there. Now we can move on to kinetic friction, right? So before we had the kinetic friction of block B acting on block A. Well, now we're looking at the inverse of that. Okay, we're looking at the kinetic friction of block A grinding on block B as block B tries to move to the left. Okay, and then so this accounts for the kinetic friction between the two blocks, but there's one more friction that we have to account for, and that's the friction between block B and the table, and that would be this one. Forgive me for the similarity between these two colors here. I apologize if that's hard to see, but here we have the kinetic frictional force as a result of block B moving against the table. So two distinct different kinetic frictions that we have to account for. If you ignore them, you're going to end up in the wrong territory. So with that in mind, we have all the forces here. Let's move on to the sum of forces on block A, because remember, we're trying to get to F. That's the goal. You might think this is kind of a futile effort to start with block A because there's not even F in here, but that's okay. No worries. Maybe we'll get something useful like the tension or something that we can bring into block B. But you're free to start with whatever you like. Here, I'm going to summon F equals ma into the arena, where m is the mass of block A specifically. And let's see, we move on to the sum of forces in the x direction first, and that's pretty simple, very easy to see here. We've got T pointing in the plus x direction, and then the kinetic friction as a result of block B grinding on block A in the negative x direction. So that's pretty simple here, and there is no acceleration occurring, so it's equal to 0. And you might think, well, really, and we're using kinetic friction instead of static? Yes. Remember, we're kind of pulling on object, or on block B, and so it's already starting to move, and hence that's kind of why we're using kinetic friction as opposed to static. But anyway, sorry. Let's take this expression here, and we'll take this term and flip it over to the other side, so that we now have an expression for the tension. Okay? And we know what the expression is for the kinetic frictional force. Well, that's mu sub kn. But we have to be careful. We'll label n with the appropriate kind of notation here. You can label it whatever you want, but honestly, we don't even know what it is yet, because we haven't moved into the sum of forces in the y direction. So let's put a pin in this expression right here and come back to it once we know what n is. So moving into the y direction, things are very simple, very easy. You have the normal force pointing in the plus y direction, opposed by the weight of block A. And since there's no acceleration in the y direction, we can just take this weight term, bring it over to the other side, and hey, now we know what the normal force of block B grinding or acting on block A is. It's just the weight of block A. So let's plug that in over here. It looks like my prediction was correct. We came out with an expression for the tension, but not the force. But that's okay. I mean, both blocks utilize tension, so it'll come in handy. We'll see it again, I promise. Let's move on to the sum of forces in block B. Okay? F equals ma. I choose u. Come back. So we have the mass of block B specifically in this expression now, and we're moving on to the sum of forces in the x direction. And all the kinetic frictional forces in tension point in the plus x direction, so they're all positive, and F is negative. Okay? And remember, block B is getting pulled on at a constant speed. constant speed means acceleration is 0. So there's no ma term. It's just equal to 0 on the right-hand side. And since the whole goal of this problem is to solve for f, well, we can make it easy on ourselves and just move f to the other side. And now we just have to decipher what all this stuff is and try to get to some variables that we know. What can we do? Well, first thing we can do is we can exchange the force of kinetic friction for mu sub kn using the appropriate n's, right? So, you know, if there's B here, B goes down here, A on B goes down here. So nothing new. And I don't want to keep writing F over here. You know, it should kind of be apparent. So I'm just going to leave this blank on the right-hand side. It's going to be representing F. Just a heads up there. What can we do now? Well, not much. Because again, we don't know what these normal forces are equal to. So let's slide into the sum of forces in the y direction, and what should we try to solve for first? It's kind of a good question. Well, both of these terms are negative, and I don't like negative stuff, so let's flip it over to the other side, and now we have an expression for one positive thing being some other positive things. So it's at least visually pleasing. We can take this information here, and in fact, on the last slide, we came out with an expression for what this was, the normal force acting on B. That was just equal to the weight of block A. So in fact, the normal force of block B can be broken down even further. It's just the sum of the two weights. Okay? So that's cool. We can take this and plug this in over here and try to utilize that in some way. And in fact, I'm running out of space here on the screen, so I'm going to combine these terms kind of like this and write them this way. Just so you know, it's the sum of two weight terms. We'll have to come back to that in a little bit here. But with that in mind, I'm going to replace NB now with this sum of these two weights. So that's what this line looks like, and it's still equal to F. I'm just not writing it every single time. And what can we do next? Well, remember, before we said that the normal force of block A acting on block B, that's equal to the weight of block A. And if that's what this term is over here, well, why don't we just plug that in as well? So let's do that next. So now we're starting to approach something that looks workable. However, what about this T, right? Let's get this out of there. We don't know what the tension is. We said that the tension was equal to the coefficient of kinetic friction multiplied by the weight of block A. So if I plug that in the next line, well, hey, now I'm moving towards something that I can work with. I know what the coefficient of kinetic friction is everywhere, and I know what all the weights are. So that's pretty sweet. Now I can get to F. In fact, we can sum these two terms together and simplify this expression even further. And because I'm running out of screen here on this particular slide, I'm going to take this last expression here and kind of rewrite it on a fresh one like this. So we have F being equal to what that last line was on the previous slide. And remember, we said that this WA plus B, I wrote it like that because everything was getting kind of like, you know, filled up on my screen, and I just needed a compact notation. So let's break it apart again. And we see here that, you know, we have mu sub k multiplied by both weight terms, and then we're also adding mu sub k times the weight of the block A. So we can just add this one to the other one, and now we have mu sub k, weight of block B, plus 3 times mu sub k times the weight of block A. I know all this. We were given all that information, so we're done. We don't need to go any further. If I plug all this information in, what do I get? Well, It's equal to 2.97 newtons exactly on my calculator. However, in the problem description, they threw us a curveball. The significant figures for the weights has 3 values, right? Because the 0 after the decimal point is considered significant. So 1, 2, 3. 1, 2, 3. However, that's not the case for the coefficient of kinetic friction. This 0 is not considered significant. Only the one after the decimal place is. So we need to report our answer, this 2.97, to 2 significant figures to match what was given to us in the problem description. Otherwise, you're going to get it wrong. So if we do that, it just comes out to be 3, which is a lot, nicer looking than 2.97. And that is it for this problem. Thanks for watching.